Imagine for a second opening your news app and seeing the headline, Hints of Life Found 90 Million Miles from Earth. What would you do? Would you laugh, shrug, or let your mind race into the unknown? Well, buckle up, because today we're talking about K2-18B, and it just might be the most compelling exoplanet news in years. There's an electric sense right now that this isn't just another maybe story. It's different this time. So let's jump right in. K2-18b, discovered back in 2015, orbiting a red dwarf star in the constellation Leo, about 124 light-years away. This planet sits in that coveted Goldilocks zone where liquid water might just exist. And it's not a little rock like Earth, it's a sub-Neptune, a planetary class we don't even have in our own solar system. That means it's about 2.6 times the diameter of Earth, with 8.6 times the mass. Weird, right? Already we're dealing with something fundamentally alien. Now, why are so many eyes on this particular world? Sure, it's in the habitable zone, but so are plenty of others. The real attention comes from what's been detected hovering in its atmosphere. Using the James Webb Space Telescope, the JWST, the telescope everyone's talking about, astronomers caught a glimpse of certain gases in K2-18b's sky that got everyone asking the same question. Life or something else? Here's the kicker. Those scientists saw spectral hints, light fingerprints, of dimethyl sulfide, DMS, and maybe also dimethyl disulfide, DMDS. If you've never heard of those, here's the cool part. On Earth, DMS is strongly linked to life, mostly churned out by ocean plankton. So we're wondering, if it takes living things to make this stuff on Earth, is that also true 124 light-years away? And it's not some shaky one-off measurement either. The first possible DMS detection came from JWST in 2023, but the signal was too weak to be convincing. Fast forward to April 2025, when astronomers went back with JWST's MIRI instrument, which looks at longer wavelengths. This time, the absorption features, the little dips in the light signal, were strong, clear, and reached a significance of 3.4 sigma. Maybe that sounds like science jargon, but in plain terms, it's a pattern in the atmosphere that's very unlikely, about 1 in 370 chance, to be just a fluke from random noise. And the best models to explain this new data require unexpectedly high DMS or DMDS, about 10 parts per million. How high is that? On Earth, atmospheric DMS is way, way lower, less than 1 part per billion, so we could be seeing thousands of times the Earth's level out there. But why all the drama? Because finding these gases doesn't automatically mean, aha, aliens. That's the tension. In exoplanet science, a biosignature is any sign that, as far as we know, can only, or overwhelmingly, be produced by life. But to actually claim something's a biosignature, you have to rule out every mundane explanation. Not most, every single one. And as we learned with supposed phosphine on Venus and methane on Mars, that's a very tall order. Let's have a quick flashback. Remember the phosphine on Venus story? Big headlines in 2020, wild speculation about bugs in the clouds, and then reality check. Turns out the signal might have been processing error, or just a different gas, and there were plausible non-biological ways to make it. The Mars methane saga? Same thing. There's faint, variable methane, sometimes linked to life, but also just as likely from rocks or sunlight-driven chemistry. Each time the story goes viral, then gets doused with buckets of scientific caution. So what sets K2-18b apart? Two things. First, it's not just one instrument or one observation. The DMS signal was hinted at with near-infrared measurements in 2023, then re-examined and found even stronger with the mid-infrared MIRI data in 2025. Second, if the signal is real, the sheer abundance is something we don't easily see from non-biological processes. But, and this is a gigantic but, we are talking about a planet completely unlike any in our neighborhood, and the chemistry could be just as alien. How could DMS or DMDS show up abiotically? We know now that it can happen without life. DMS exists in interstellar clouds, on comets, and experiments have even created it in labs simulating exoplanet atmospheres. just zapping the right gas mix with UV light or a spark. So on K2-18B, maybe there's some wild volcanic chemistry, or the immense pressure and different atmosphere allow reactions never possible on Earth. Maybe there's lightning storms or exotic mineral reactions. The bottom line, just because something means life here doesn't make it a universal rule. We also have to deal with the numbers. 3.4 sigma is interesting, but in scientific discovery, people usually demand 5 sigma. That's roughly a 1 in 1.7 million chance of a fluke before anyone pops the champagne. Why? Because errors, unknowns, and wishful thinking have fooled us before. And on a planet this far away, where we can't tweak variables directly, caution is justified. So what would it actually take to close the case? More JWST observations, for starters, so more telescope time, watching more transits, getting that statistical certainty way higher. More detail in the measurements might finally separate DMS from DMDS. And absolutely, other independent research teams need to chew through the raw data, check for subtle errors, and, frankly, try to break the result. Meanwhile, modelers and laboratory scientists are going into overdrive, trying to simulate every conceivable non-biological chemistry that could explain this. If known chemistry can't make this much DMS or DMDS, and if the 5 sigma standard is met, and if multiple teams confirm the atmosphere is real and not some statistical ghost or instrument glitch, then we're in new territory. Let's step back for a second to look at the planet itself. K2-18b is odd, even for exoplanets. Its density is much lower than Earth's, and that suggests it's not just a giant ball of rock. It probably has a thick hydrogen atmosphere, the kind we do not see on any rocky planet in our solar system. This led to the Hycean superocean idea, a world with a planet-wide water ocean, hundreds of kilometers deep, shielded by heavy hydrogen. That's a radical concept. But the truth? It's not proven. The planet is big enough that, by some models, it ought to be more like Neptune. Lots of ice and gas, with no true surface ocean at all. And even if it has an ocean, the thick atmosphere might create hellish surface temperatures and pressures. So the biggest question, is this a cozy ocean for life or a boiling, crushing nightmare? So let's say for argument's sake that the DMS detection is real, and let's say there is a habitable ocean. What would life look like? Sorry, no little green folks. We're talking microbes. Think Earth's phytoplankton or bacteria. If there's life, it's almost certainly simple, microscopic, and living in alien seas under starlight so different from ours. Scientists are marching forward on every front. More JWST observing time has been suggested. Something like 16 to 24 more hours could push the evidence past that critical threshold. In the coming year or two, depending on telescope scheduling, we might see answers. Meanwhile, theorists are working overtime to simulate and recreate K2-18b's environment in the lab, to see if they can whip up DMS in those weird conditions without life. Zooming out, this isn't just about one planet. JWST is utterly transforming how we search for life. Coming up, even bigger telescopes from the ground and space, like the Habitable Worlds Observatory and extremely large telescopes, will give us sharper tools and a clearer view, hopefully cutting through the haze to reveal what's really going on. What's the mood among the experts? Cautious optimism, excitement, yes, but paired with a hefty dose of skepticism. Some researchers think the planet's simply too big or too hot for habitability. Many point to the statistical uncertainty. And everyone agrees we need independent confirmation and ironclad modeling of non-biological chemistry before using the L word. Because here's the deal. If K2-18b is truly home to life, even microbial, it's a paradigm shift. It would prove for the first time that Earth isn't unique, that life can take hold on other worlds. It would validate decades of hard scientific work, open up the field of comparative exoplanetary biology, and utterly reshape our sense of place in the cosmos. But what if it's not? What if it turns out to be wild chemistry fooling us? Even then, we win. Every step in this process, every check, every failed hypothesis, pushes us further in understanding our galaxy's diversity. We learn more about the limits of habitability, about chemistry under alien skies, about where to look next and how to look smarter. Let's end on a little food for thought. K2-18b orbits a red dwarf star, not our familiar sun. That means it lives in an environment bathed in red light, with closer orbits and likely wild temperature swings. Flares from its star could impact the atmosphere, the climate, maybe even life's odds. Everything about this planet challenges our Earth-centric way of thinking. And even as we chase familiar molecules like DMS, we need to remember life beyond Earth could be utterly unlike anything we know. It might use totally foreign chemistry, depend on substances as unremarkable to us as water is to a fish. Our search is always going to be haunted by the limits of our imagination. So here's the big takeaway. K2-18b, as of right now, isn't proof of alien life, but it's the best hint we have and a call to action for science, curiosity, and rethinking our place in the cosmos. Watch this space, literally. The next chapter could arrive sooner than you think. And now I'll leave you with this. If one day soon we confirm even the simplest life on another world, what would that mean to you? How would it reshape your sense of belonging, your view of possibility? Are we the rule or the exception? The universe is whispering back. Are we ready to listen?